This video is a review of slope fields and separable differential equations. These problems are calculator active, so we will be using our graphing calculator as needed. Number 1. Consider the differential equation dy dx equals 1 over x. Which of these shows a slope field for the given differential equation? This one should be relatively easy because it is only in terms of y. What if y is 0? Then we'd have 1 over 0, which is undefined. That means we should have a vertical slope. So, which of these has a vertical slope when y is equal to 0? So I'm looking at the x-axis for part A, option A, I see vertical slopes, so that one's okay. There are no vertical slopes on option B, so that's out. No vertical slopes here, that's out. D has it, so we've narrowed it down to A and D. Let's do another test value. What should the slope be when y is equal to 1? Well, that's going to be 1 over 1, which equals 1. So at a y value of 1, we should see a bunch of slopes that are positive 1. These look like negative 1, so that's out. That just leaves D, and check it out. Positive 1. Brrr. So the answer is D. Number 2. Which of the following gives 2 possible solutions to the given differential equation? You can use the slope field to answer your question as opposed to trying to solve it by hand. We know that natural log graphs look like this. That's a better match for option C, which was not the answer, and not so much D. We know that square root graphs look like this, which is a better match for the slope field D. So we can forget about options A and B. It's going to be one of these two. Options C and D both include the parent function square root of 2x, which would look like this. So it comes down to the square root of 2x plus 3 versus the square root of 2x plus 3. Quick side lesson. Let's say you have parent function f of x that looks like this. If you add 3 to the outside of the function, it moves the graph up 3, like this. Adding 3 on the inside of the function moves the graph 3 units to the left. So in option C, the parent function is being shifted 3 units to the left, while in option D, the parent function is shifted 3 units up. Which one of those transformations would give us another solution? This slope field seems to suggest variations of the same solution, just shifted left or right. So shifting the parent function left 3 units would be another solution. So the answer is C. Number 3. Verify that y equals sine 2x is a solution to the differential equation 4y plus y double prime equals 0. Well, if y equals sine 2x is a solution, then 4 times y plus y double prime should equal 0. So let's find y double prime and plug it in and see if we get 0. First, we need to find y prime. The derivative of sine is cosine, but because it's not just x on the inside, I have to use the chain rule and multiply by the derivative of the inside, which is 2. I like to put the 2 in front, so now we have this. Now let's find y double prime. I'm bringing down the 2. The derivative of cosine is negative sine. So I'm going to put the negative, and then I have sine. And again, the chain rule, I multiply by the derivative of the inside, which will be 2. So that's going to be y double prime is equal to negative 4 sine 2x. So let's plug it into the original equation and see if we get 0. So we're checking to see if 4 times y, and remember y is sine 2x, so I have 4 sine 2x plus y double prime, so that's negative 4 sine 2x, and does that equal 0? Yeah. They cancel each other out, so it checks out. Number 4. Which of the following differential equations is modeled by the given slope field? Well, looking at option A, y squared is always positive, so there would be no negative slopes, and I do see plenty of negative slopes around, so A cannot be the answer. 1 over x squared is also always positive, so for the same reason, it cannot be C. If B was the answer, whenever y would equal 0, then we'd have negative 0 squared, which is 0. So the slope would be 0. Y is equal to 0 all along here. All of these would have a slope of 0. And that is clearly not the case. I mean, it's super obvious when you look at these two, for example. The slope is not 0. So it can't be B. Similarly, E cannot be the right answer. We have y in the numerator. So whenever y is equal to 0, the fraction, the slope, should equal 0, other than when x itself is 0. But everywhere else, the slope should equal 0. And as I just mentioned before, like here and here, y is 0, but the slope is clearly not 0. So E cannot be the answer. So the answer is D. Number 5. If y equals f of x is a solution to the differential equation whose slope field is shown in the previous question, which of the following is also a solution? Can you see how the slope field suggests variations on the same solution that are just being shifted up or down? So which one of these options suggests a transformation that is either up or down? Option A is a transformation of 3 units up, so the answer is A. Number 6. Given dy dx equals y over x minus 1, show that the second derivative is equal to negative 1 over x. To find the second derivative, you take the derivative of the first derivative, and I'm going to differentiate term by term. So as I take the derivative of the first term, I'm using the quotient rule, which goes low d high less high d low. Draw the line, and down below, the bottom squared will go. What was that again? Well, when I say low d high, I mean low is x, and d high is the derivative of the numerator. So that'll just be dy dx. So that's low d high. Less means subtraction. And now I'm going to say high d low. High is just the numerator, and d low is the derivative of the denominator with respect to x. So that's just 1, so I don't need to write that down. Draw the line, and down below, the bottom squared will go. So there's your quotient rule. When I take the derivative of 1 with respect to x, that's going to just be, well, it's 0. So we write nothing. Now I need to substitute. We have this dy dx right here, but we know that dy dx is supposed to equal all of this. So let's make that substitution and see if we get negative 1 over x. So now I have this. On my next step, I will distribute this x across the parentheses. When you multiply x times y over x, the x's cancel out and you just get y. And then x times negative 1 is negative x, and we still had the negative y. I see like terms here. We have y minus y, so those will cancel each other out. So now we have this, but the x in the numerator will cancel out one of the x's in the denominator, and we see that the second derivative equals negative 1 over x, which was the target. Number 7. A particular solution to the differential equation dy dx goes through the coordinate 2, negative 3. At this point, the graph of the solution is which of these? It's all about concave up versus concave down, and increasing versus decreasing. Back in Unit 2, we learned that the second derivative will give you the concavity of the original function at a particular point. If the second derivative is positive, the original function is concave up. If the second derivative is negative, the original function is concave down. So let's evaluate the second derivative at the point 2, negative 3 and see what's going on. So it's just negative 1 over x, so the negative 3 is not relevant. It will be negative 1 over 2. So at this point, the second derivative is negative, which means that the original function is concave down. Looking back at the options, that allows us to throw out option A and option B. Back in first semester, we also learned that the first derivative will tell us whether or not the original function is increasing or decreasing. If the first derivative is positive, the original function is increasing. If it's negative, then the function is decreasing. So let's evaluate the first derivative at 2, negative 3 and see what's going on. So here is the first derivative. It's y over x minus 1. So that's negative 3 over 2 minus 1. This is clearly less than 0. So that means since the first derivative is negative, the original function must be decreasing. So concave down and decreasing, the answer is D. For number 8 through 11, consider the differential equation dy dx equals x plus y squared. Number 8, on the axes provided, sketch the slope field for the differential equation at the 9 points indicated. At the point negative 1, negative 1, we would have negative 1 plus negative 1 squared, and that's negative 1 plus 1, which is 0. So we should have a horizontal slope at negative 1, negative 1. At the point 0, 1, we have 0 plus 1 squared, which equals 1. So right here we should have a nice 45-degree slope. At the point 1, 1, we have 1 plus 1 squared, which equals 2. So we should have a slope that is steeper than a 45-degree angle right here. At the point negative 1, 0, we have negative 1 plus 0 squared, which equals negative 1. So we should have a decreasing slope that is at a 45-degree angle right here. At the point 0, 0, we have 0 plus 0 squared, which equals 0. So we should have a horizontal slope right here. At the point 1, 0, we have 1 plus 0 squared, which equals 1. So we should have a slope with a 45-degree angle right here. At the point negative 1, negative 1, we have negative 1 plus negative 1 squared, which is really negative 1 plus 1, which equals 0. So we should have a horizontal segment here. At the point 0, negative 1, we have 0 plus negative 1 squared, which equals 1. So the slope should be a nice 45-degree angle right here. And finally, at the point 1, negative 1, we have 1 plus negative 1 squared, which is 1 plus 1, which equals 2. A slope of 2 is steeper than 45 degrees, so your segment should be steeper than these two. Number 9. Let y equals f of x be a particular solution that goes through 1, 2. Find the tangent line to this particular solution at the point 1, 2. Whenever we find the equation of a tangent line, we always use point-slope form. So all we need is a point and the slope. And in this case, they gave us the point. The point of tangency is 1, 2. So all we really need is the slope. We can find the slope using the first derivative. So we just need to evaluate dy dx at the point 1, 2. So that's just going to be 1 plus 2 squared. That's 1 plus 4, so that is 5. Now that we have a point and the slope, we can easily write the equation. it goes y minus y is equal to the slope times x minus x. Easy peasy. Number 10. Use a tangent line approximation to estimate f at 1.2. To use this tangent line to estimate the value of f at 1.2, it will be more convenient if we get y by itself first. So, distributing the 5 across the parentheses, we have y minus 2 is equal to 5x minus 5. Adding 2 to both sides, we have y is equal to 5x minus 3. So f at 1.2 is approximately equal to 5 times 1.2 minus 3. And that's 3. Number 11. Assume the particular solution is concave up in the first quadrant. Is your estimate from the previous question more or less than the true value of f at 1.2? Justify your answer. If a function is concave up, the tangent line will always be below the curve. So any estimate will be an underestimate. The tangent line approximation is less than the true value of f at 1.2 because the particular solution is concave up in quadrant 1. Number 12. Given dy dx equals 2xy, find the particular solution that goes through 0, 3. This is a separable differential equation. So let's get all of the y's on the left side of the equation and all of the x's on the right hand side. As a first step, let's multiply both sides by dx. So we will have dy is equal to 2xy dx. So I would like to get this y over on the left. So I'm going to divide both sides by y. So over on the left, I will have 1 over y dy is equal to 2x dx. Now that we have the y's on the left and the x's on the right, we can integrate both sides of the equation. For the integral of 1 over y, we can use the memorized rule that this is the natural log of the absolute value of y. Normally I would say plus c, but I will do the plus c on the right-hand side of the equation. For the antiderivative of x, I would do x squared, and then I would divide by the new exponent. But 2 divided by 2 cancels out, so I just have x squared plus c. Now we use the initial condition to find the value of c. Let's put in 0 for x and 3 for y. So the natural log of the absolute value of 3 equals 0 squared plus c. But this means c is equal to the natural log of the absolute value of 3. Substituting this back in for c, we have this. This is the particular solution of the differential equation that goes through 0, 3. Number 13. Which equation below is the same as your answer above if we assume y is never negative? So let's solve for y. We will not need the absolute value symbol since we're assuming that y is never negative, and we didn't really need the absolute value symbol here at all because 3 is obviously positive. So we want to get y by itself. We can get rid of the natural log by exponentiating both sides of the equation. In other words, drop a base e on both sides. Base e and natural log are inverse functions, so they cancel each other out, and it leaves you with y equals. So really, I have y equals this, but the reason why I'm not just writing that down is because I see that that doesn't match any of my answers. So I'm going to have to do something to this. So what am I going to do? Well, let's do a quick side lesson. If I have e to the n power times e to the p power, we know that when you multiply like bases, you add the exponents. So that would give you e to the n plus p power. But this is reversible, so if I have e to the n plus p power, I can rewrite this as a product, e to the n power times e to the p power. And that's what I have going on over here. So let's rewrite this as a product. E to the x squared times e to the natural log 3. Again, the base e and natural log are inverse functions, so they will cancel each other out and just leave a 3. And I will put this 3 in the front and bring down e to the x squared. This matches option D. Last one, find the general solution for the following differential equation in the form y equals f of x. dy dx equals 4 sine x over y. This is a separable differential equation, so let's try to get all of the y's on the left side of the equation and all of the x's on the right hand side. A good start would be to cross multiply. So if I do that, on the left hand side I'm going to have y dy, and on the right hand side I will have 4 sine x dx. Well, that's it. We already have the y's on the left and the x's on the right. So we can go ahead and integrate both sides of the equation right now. The antiderivative of y will be 1/2 y squared. I'll save the c for the other side of the equation. The antiderivative of sine is negative cosine, so I'm going to have negative 4 cosine x plus c. This is a general solution to the differential equation, but we want it in the form y equals f of x. So we just have to get y by itself. Let's start by multiplying both sides of the equation by 2. So we will have y squared is equal to negative 8 cosine x plus 2c. Now we will take the square root of both sides of the equation. So we will have y is equal to plus or minus the square root of negative 8 cosine x plus. 2 times a constant is just another constant. Let's call it d. This is the general solution of the differential equation in the form y equals f of x. You could leave 2c instead of d if you wanted to.